biggest explosions in the universe come from some of the smallest stars. They illuminate the universe and the processes that have occurred since the dawn of time itself. And today, we're going to explore the physics of these stars, so-called supernovae, how they came to be, the deaths of stars, and the birth of the universe. Inside every star is a battle between gravity, tending to compress it, and the repulsive force of photons escaping outward. These photons come from nuclear fusion. This process produces heat, and the star is in balance. This balance can last for billions of years. Some stars don't have a thermonuclear core anymore. They've gotten quite old, and this type of star is called a white dwarf. Some of the white dwarfs are hypothesized to have within them pure carbon, which could be in the form of a diamond, as shown here. And this entire star, weighing as much as 140% of the mass of our sun. This white dwarf can be the same size as the Earth, which is 1,000,000 times smaller than the sun. So a white dwarf is a dead star. It's no longer undergoing photonic production because it's no longer producing fusion at its core. They're held up by the pressure, the mutual repulsion of electrons in a degenerate quantum state. As you add in more mass, they get smaller. This is a particular and peculiar state of matter called highly degenerate matter. Now, supernovae are going to play a role, as they have throughout the history of cosmology, illuminating processes that are extremely violent. Supernovae have been observed throughout our history as a species, perhaps from thousands of years ago, right up until the 1980s, when I was a wee lad getting ready to go to college. This supernova, called Supernova 1987A, went off in the Large Magellanic Cloud, which is a satellite galaxy of the Milky Way, and was observed by astronomers. And some people have wondered what would happen if a supernova went off much closer to us than the Large Magellanic Cloud, which is hundreds of thousands of light years away from the Earth. Well, it could be really quite disastrous for life on Earth. A type 1a supernova is incredibly important for our understanding of the luminosity distance to distant objects, which is how cosmologists determine that the universe is not only expanding, but the rate of expansion is increasing, i.e. accelerating, revealing in turn the presence of dark energy. A type 1a supernova is a bomb in space. It's the explosion of a white dwarf in a binary system. The binary system could be another type of star, say depicted here, a sun-like star, which has its matter sucked by these vampires called white dwarfs. White dwarfs have incredible tidal gravitational forces. You could also have a white dwarf merging with another white dwarf. And as this occurs, the eventual time will come when the white dwarf has a mass greater than the Chandrasekhar mass limit of 1.4 times the mass of the sun. At such a mass, the system goes supernova and explodes. Now, this type of process, which is incredibly luminous, is to be distinguished from what's called a type 2 supernova. A type 2 supernova is really thought of as another type of bomb, but a gravitational bomb. It's a bomb that results when the outer layers of a star collapse onto its core. This occurs when a star ceases being able to provide that pressure to counteract the gravitational infall of its matter. So these processes are very simple, even though they involve things like nuclear fusion and nuclear explosion, which are very complicated processes. But the actual physics is a mechanical balance between pressure outwardly and gravitational forces attracting matter towards itself. Once the pressure support disappears, the whole sham is up, and the star's outer layers collapse down, fall in, and eventually have a shockwave that rebounds. Now, this rebounding can produce the heavy elements that were last being produced at the core of a star. And in fact, many of these were discovered right here by my colleagues at UC San Diego, Jeff and Margaret Burbidge, who in 1957 published an epochal paper with Fred Hoyle and Willie Fowler. This was called Production of Elements in Stars, or Synthesis of Elements in Stars, known by its initials BBFH, one of the most famous papers not only in astrophysics history, but really in all of physics. It paved the way for understanding of how these stars produce the metals and elements that we're made up of. In fact, the iron at the core of a type 2 supernova, that central figure shown here, produces the source of the iron that's in our blood and the hemoglobin molecule. Without it, we wouldn't be here. But that iron came from the explosion of a type 2 supernova in our region of the galaxy some 5 billion or more years ago. Now, astronomers don't make use purely of these explosive phenomena by themselves, just the explosion itself. They also want to look at the chemical fingerprint, the spectrum of these stars. So astronomers break these two supernova types down into two main categories, type 1, type 2. But these explosions are incredibly important, and so astronomers classify them in major subsets. Type 1 supernova are broken down into type 1a and type 1b. Type 1A is distinguished, as we just described, as the thermonuclear detonation of a dwarf star in a binary system. Type 1b is the same as the previous supernova type 2 that I just described, gravity bomb, except in this case, the stars that have lost their outer layers via the puffing out of what are called stellar winds. And this is very telltale for my extremely clever astronomy colleagues. They can rapidly distinguish between a type 1, type 1a, type 1b supernova and really focus on the ones that they want to use for the particular application. When it comes to understanding the expansion of the universe and how that's accelerating, that process relies on type 1a supernova, not the type 2 supernova and not the type 1b supernova. And what we want to do for all of these is really characterize the luminosity of the object and relate it to its distance. It's hard to measure the distance to an astronomical object because we don't have a depth perception in cosmology. We're really good at seeing left and right, up and down, measuring the position to micro arcsecond precision, but it's very hard without a model that relates the redshift, which is easy to measure, and the distance, which is hard to measure. We want to come up with a relationship between those two that depends on the composition of the universe. What is contained in the universe, how much matter there is in ordinary matter like protons and neutrons, croutons, and also how much non-ordinary matter, dark matter there is, and then how much dark energy there is. So there are many types of 1A supernova that can exist. They're very bright. You can see them very far out in the distant universe. They explode at a very well calibrated amount of mass, which via the most famous equation in all of physics, E equals mc squared, once you know the mass is well established, you can convert exactly to the amount of energy produced and then calculate how much of that's in the form of light and use that to calculate how much light is observed and how much you would observe given different amounts of dark matter, dark energy in the universe. This is what cosmologists do. This then allows us, using the simple inverse square law, to measure very accurately for a known amount of luminosity the distance to these objects. Let's take a quick detour. Astronomers, for all their brilliance, have used a very obtuse way of measuring brightness or luminosity called the magnitude, going back to the ancient Greek times. There are two types of magnitude. The magnitude related to how much light is being produced by an object, and the amount of light that we on Earth or in a space telescope are observing. The intrinsic luminosity, which is being produced by the object, is going to be given a magnitude symbol, capital M, and then what we observe is lowercase m. So it's confusing because it's the same sounding word, M, and it's not the wrapper. We can construct a difference between what we observe and what was produced, lowercase m minus uppercase m. We call that quantity mu. That depends on the luminosity distance, which is hard to measure, and we relate mu to the parameters of the expansion of the universe. The Hubble expansion constant, h naught, and the so-called deceleration parameter, q sub naught. These were thought to be the only two parameters of interest in the early universe. Called by Alan Sandage, cosmology was the search for two numbers: the expansion of the universe via its Hubble constant, and the deceleration. It was thought that the universe would decelerate because there's matter, and so matter only attracts gravitationally. Why would you expect there to be anything other than deceleration for a universe, after all, which we know contains mass? But astronomers didn't find that. They found that Q was negative. What's called negative deceleration. And so astronomers use these different colored filter bands to define different wavelength regimes for different purposes. And then they ask, well, how much redshift is there for these different wavelength bands of a given type 1A supernova? And they've been doing this literally for decades. And the culmination of this was the awarding of the Nobel Prize to two past guests on the Into the Impossible podcast. We had Adam Rees, we've had Brian Schmidt on the podcast. I've yet to get Saul Perlmutter on.
We need Saul. He won't do it.
If you are listening out there, Saul, you know I've been sending you emails.
You could ask him. Hey, I could ask him.
Please do come on. In some way, they are related to a friend of ours, Bob Kirshner, who will also hopefully someday be on the podcast.
It's all good, man.
Is now taking over leadership role of the 30-meter telescope. So exciting. So the observation of these stars led to a convergence that the universe had a substantial amount of energy density in the form of a vacuum or cosmological constant, heretofore unexpected. That was the only way to explain the not only expanding universe, but the rate of change and increase in the expansion rate of the universe. This was astounding. And now, decades after the initial discovery papers, the data have even gotten stronger and more conclusive. We have the so-called benchmark model that depicts a universe that at very early times was dominated by heat, by the energy of photons that would later become the CMB. And slowly thereafter, about 200,000 years after the Big Bang, became dominated by matter. And then only a few billion years ago, so maybe 10 billion years after the Big Bang, did dark energy take over and become the dominant force of expansion in the universe. So photons and matter actually cause the universe to decelerate, to get smaller and smaller Hubble constants over time. And dark energy does the opposite, causes the Hubble constant to increase. So therefore, looking at different redshifts, you will expect to see different phenomena. It's unequivocal. These data points, as I say, keep getting stronger and stronger. You can read about the discovery of this in a wonderful book by Bob Kirshner called The Extravagant Universe. And going through the different phenomena that we could expect to see, the universe could have been either expanding forever, it could be coasting, it could have never started to expand in the very beginning. All these phenomena were ruled out by these observations in combinations with measurements of the omega matter component as shown here. The omega matter component is very accurately traced by phenomena like the cosmic microwave background anisotropy, which will be spoken about in upcoming videos, and it can be measured by so-called baryon acoustic oscillation observations, both of which trace the processes of ordinary matter, which we call baryonic matter, and non-ordinary matter, which we call dark matter, really a stand-in, a placeholder for unknown physics that we don't understand. So here's what a supernova looks like. At different times, a supernova will peak at a certain time, and then the brightness will decay over time. So this is showing the light curve decay. This is coming from Bob Kirshner. These observations at different timescales will be tracing out a very characteristic curve that astronomers like Bob and his colleagues have characterized very well over the decades. So you can actually see the supernova can be actually brighter than the galaxy that's hosting it, which is quite amazing. And these characteristic curves are traced out for all sorts of supernova and all sorts of wavelength regimes. Shown here is different colors at the same time scale, and you see different phenomena that take place. And it's actually possible to distinguish between the supernova's behavior in its visible or optical light wavelength bands versus the infrared bands shown here. And it actually looks different in the infrared versus the optical. In the optical, it clearly has just one hump, one peak, and in the infrared, it has multiple humps or multiple peaks, giving you multiple bites at the cosmic apple, understanding how the universe has been expanding since the supernova have blown up. What do we do with supernova cosmology? We start by measuring the magnitude, brightness of a given exploding star. Once we know it's a type 1a, we measure the light curves as a function of time in as many wavelengths as we can. That's a technical challenge, but
That's technical talk. That doesn't really concern me.
astronomers are really good at solving those technical challenges. They measure the redshift from the spectrum. You take the inferred distance modulus, which is the magnitude that you observe, lowercase m, minus the intrinsic magnitude, uppercase m, which comes from a model. You construct that and compare that for as many different type 1a supernova as you can measure, and you make a so-called Hubble diagram, plotting the distance modulus, mu, as a function of redshift. And then you compare those to a theoretical model which will predict the distance modulus at a given redshift for a given cosmological combination. You put in different ingredients, different amounts of dark matter, ordinary matter, dark energy, and you mix it together and you ask, how does that affect the distance modulus as a function of redshift? You plot all those, you do a likelihood analysis, and this is what astronomers did. It sounds easy now, it was really hard back then. They got it right the first time and they won, of course, the ultimate prize. And I think it's quite striking that astronomers continue to use this, and these tools are now being used to settle another, perhaps cosmic mystery, or perhaps even raise the attention to higher and higher levels. Why do the cosmic measurements from CMB experiments, like the kind I just described, why do they differ so much from the late-time universe measurements? After all, the universe was much more simple in the distant past, in the early universe, than it is when supernovas start to form and galaxies start to cluster. They should get the same answer, but they don't. That's called the Hubble tension. We've discussed one possible mechanism, which relies on magnetic fields. Because of this, we have a very, very significant opportunity to get even more information from the late universe, observations of supernova and Cepheid variables, compare that to early measurements, perhaps with upcoming instruments like the Simons Observatory, and we will continue to discuss the Hubble tension and possible solutions to it, and possible other contributors to this cosmic energy pie chart shown here in terms of different candidates for the amount of dark energy and dark matter that we know to exist. If you like this video, please check out this video over here, where I explain the possible solutions to the Hubble tension using magnetic fields. Don't forget to subscribe.